So now with all these notations, we are ready to start talking about value iteration algorithm, which would enable us to solve MDP given the quadruple of state, action, transition, and rewards. And that's where we will utilize all these notations from above. Let me just start writing. So I will introduce a tiny bit of notation, so it's not a new notation, but I will just look at this value of the state. And when I introduce you a value of the state, I told you this is the expected reward that you're going to get when starting in the state S and acting optimally. I didn't tell you for how many steps you can go, for 1, for 2, forever, until you are done. So now I would actually cap it up. I would say that this will be an expected reward that you can get after you took K steps. Okay, so we will introduce this new notation. This is expected reward from state S after K steps. And the idea here is the following. What is the connection between this Vk and my original V value of state? That when K goes to infinity, we would say that our Vk would actually converge to the true value of the state. So the recursive algorithm that I will define will at each point continue increasing number K until we will hopefully converge to the true value of the state. Okay? So how this algorithm will work? During the first step, this will be initialization step. We will make all of our value V0, they all will be equal, let's say, to 0. Okay, and if you need an intuition of what this Vk means, okay, Vk star means, you can think progressively about our original diagrams that we had, and I will draw you this diagram again. Okay. And what you can think about is, you can think about the information from the steps, from the states where we get higher reward. It will be slowly propagating around the board. And the first time we're going to look just in one step, then in 2 steps, and so on and so forth. So, and we will continue until we reach convergence. So our next step would be to say continue, iterate until Vks, roughly speaking, equal to Vk plus 1s for all s's. So we will continue this process until the values of the states do not change after every iterations. And what we will do, we will define the value of our step of our state at the point k plus 1s in terms of the values of the states through the previous iteration. So we computed the optimal values after k steps, and now we will aggregate this information to get the value for the step k plus 1. And that's exactly the formula that we wrote over here with the corrected parentheses is going to come handy. Because here, whenever we are going to be looking at the value of the state after of the neighboring states, we can actually take the values that was collected after k steps. Okay, so we are going to say that the value that we are getting after k plus 1 steps is going to be whatever we are collecting from an extra step plus the values of the neighboring steps after k steps. So let's just write it down. It will be much more clear than just talking about it. So we're going to say max A and I am pretty much copying the formula as it is with parentheses. And now I will take the values that I have already collected, which is the value of the neighboring state S prime after k steps. Okay? So this is the whole value iteration algorithm. Let me just very briefly illustrate to you what it will be doing on a very simple and trivial example. Okay? So let's say I am given now some very simple world, and we have several, let's say 5 states, okay? And you will collect your reward, you know, in this final step. When you get here, you collect the reward and you're done. You cannot move anywhere. And you also assume, again, it's a very simplistic state, that you are always moving deterministically, that you can only take one single action, okay? And whenever you take this action, you're going to end up where you want to be. It's very, very simple state. In reality, obviously, it doesn't work, but here we can say we would only move in the right direction, and we always end up where we want to be. And I would assume that gamma is equal 1/2, okay? So what I told you earlier, that during the step 0, all the v's are going to be equal to 0. That's how I start. I initialize all the value of the steps to be 0. Now, during the next step, what I am going to be doing, I am going step by step, and I am trying to see how my value is updated. It doesn't matter in which order I start doing it, correct? Because here you don't order the states in any way. Why it doesn't matter? Because we'll be only looking at the values of the previous iteration. So therefore, it doesn't matter if I start computing V1s from here or from here, it's exactly the same. So let's say I am here and I want to compute value of the states going somewhere by one step. I'm allowed just to walk one step further. So in this case, if I go one step further, then the value of that step is going to be 0. Okay, I'm not collecting any reward there because there is 0 reward. So this becomes 0. And the value of the state stays exactly 0. Nothing changed. And similarly, if I'm continuing walking and walking and walking 0, 0, 0, the only place where something is going to change is going to be the last step. Why? Because I know that whenever I try to walk right, which means that I'm staying in the same place, I am going to collect this reward. This is the reward that I would collect when I'm trying to go right, and I'm staying in the same location. So now this step, because of this value, becomes +1. And let's say it's a halting state, meaning that I cannot go back and forth and increase the number. Once I collected it, I cannot do it again. It's like if you got A in the class, you could just do it once for the same class. So now we can look at how the value change when we are allowed to do 2 steps of within our iterations. So here, let's again start in the order here doesn't matter, because when I'm looking at the value of neighboring states, I'm just looking at the previous step. So here, nothing really changed because the neighbors are still 0. Okay? So here we're going to see some interesting development. First of all, as I told you, from this state, whenever we go right, we collected the reward. I requested that once we collected the reward, we cannot get it again. The state is going to stay +1. Now let's see what happens here. This is an interesting state where we see some development. So we will go right because we're just allowed to take one action. We're going to go right. We will not collect any reward because I didn't provide any reward when you are jumping. However, this is the part that gets activated because the VK, the V1 of the previous state is +1, and I will multiply it by my gamma, which is half. So in this case, the value, of the state is going to be 1/2. Okay? And we can continue now. And if we will continue, we can again see how this value will continue propagating. I will not do this complete computation and it will be left as an exercise, but you would see that with every step the number of non-zero entries is going to increase and the values here are going to increase until at one point we will not see any change. Now I want you, of course, to remember that this was really a baby world where all was set in, where we go and we have just one action to take. Never happens in reality. And in this case, we will see much more complex interaction between the values because you can go in different directions, so they will start really impacting each other. The fact that we stabilized here and it doesn't change is just a side effect of a very simple world that I designed you, but it shows you the high-level intuition. We will start with the states where the big reward or punishment allocated and they are going to propagate it all around, and we will continue until convergence. So I want to talk to you a bit about convergence because you can ask me, how do you know that it's going to converge? And I will not do the full convergence proof here. I want to look again in a very simple world just to give you an idea how the full-scale proof may look like. So we will talk a bit about convergence now, okay? And the world that I will look at convergence would be similar to this world, even simpler. I would assume that I have a single state S and a single action A, okay? It's really a baby situation. Okay, so what I would know if I have just a single state, that V star of K plus 1 of this state S, correct? So there is no mass because we just have one single action. It's going to be RS plus gamma V star KS. Okay, so let's just see that we understand. Again, we don't need to average over different possible destination because we're going to end up always in the same state because we just have one state plus gamma and the value of the state after k steps. Okay, now what I also know from if I am already converged, when we totally converged, this is a situation that we underline here. You remember when our number of k steps ran to infinity, and now we have true values of the state. What we know is that when I am in the converged state S, that when I take my next step, nothing is going to change. So I also know that it's equal to V star S. Because this is my stop condition when we don't continue, when my previous iteration, the current iteration, have very close values. So now what I will I will subtract the converged value from the value in k plus 1 iteration, and similarly the converged value from Vk, and I will compare them, okay? So what I'm going to do is actually take the first row and subtract it from the second. V star S minus V star K plus 1 S equals gamma V star S minus V star KS. So let's look at these quantities. Here we are looking at the difference between the converged state and the value at step k plus 1. Here we're looking at the difference between converge state and the value after k step. And what we see that at every single step, the difference between them is determined by this gamma, which is the value between 0 and 1. So what it means is that at every step, the distance between our computed value k and the true converged value v is decreases, and gamma will determine the rate with which this decrease will happen. So, and this is kind of a baby case, but you don't have to look into how this may be working in a more complex scenario, but this is exactly the same intuition that shows us as we continue and increase the number k of steps, we're getting closer and closer to the values v, which are optimal values v. Now, the next step for us, hopefully I convinced you that this algorithm will converge, and if we will continue doing enough of this interaction, at some point we will stop. And now you may be asking yourself a question, okay, now I have v, how do I actually act, correct? Because value v doesn't tell you what you should be doing. And at that point, to decide what you should be doing is actually, I want to bring back our Bellman equations again and remind you that in this case, we can actually compute all the q's. Given v's, we can compute the q's, correct? Because q's are defined in terms of v. And once we computed all the q's, we can actually, for every state, find the best possible action. That's what we will do. So the next step, when we completed this algorithm, we will compute for every state S and for every action A, we will compute the q values. And once we have all the q values computed, we can actually say that the action S that we need, the action A that we need to take in state S will be just argmax A Q star SA. What it says, for given state S, go select, check all the Q star SAs and select the action which maximizes it. So what eventually I got after this algorithm, when it converged, I computed the Q values and then I computed the policy. And now I know how to act in my MDP. So that's what we have done here.